Three, two, one. Alright. Okay, here we go. The pre-recorded video for today, the 13th of February, in Math 3170, the spring 2025 semester. Alright, so last time we talked about the notion of a spanning set, which we'll revisit here in a moment. I'll fix that in a second. And then we'll follow our nose a little bit further on that. That'll lead us to this notion of linear independence. So let's get right to it. All right, so let's recall that the span of a list of elements hanging out in Rn. So recall that given those elements in Rn. We can form the span of those things by scaling and adding them together. All right, so we introduced this notion last time, and then we asked, like, all right, well, certainly you can create this set, but what does this thing really look like, right? So again, this is a completely valid collection of math symbols, but, okay, what is it actually? Like, what does this, like, look and feel like? So we computed some examples, and it was a lot of fun. And today, let's start off with another interesting example. So before we had an example that spanned all of R2, and then we looked at an example that did not span all of R3, but we were still able to sort of, determine what it sort of looks like. And let's go ahead and look at another span in R3, but this time we're going to pick some elements and something very different than what happened before is going to happen. Right. And by that, I mean what exactly? Well, before, when we were taking our spans and simplifying them, we were always having the same number of elements, right? So those two that we looked at, we had two things that we're looking to span, because as we learned, spanning one element isn't particularly that exciting. It's just the collection of all scalar multiples, so line going for the origin is the way to think of that. So it's of interest to look at the span of more than two elements, and obviously one more than two is three. Okay. Right, we were looking at the span of one element, it's pretty boring, and we look at the span of two sets of two elements, and so some interesting behavior, but now I'm going to look at the span of these three right here. My particular favorite collection of three vectors in R3. Now, if you let your mind float back to the last class, the way that I'm going to recommend that you compute the span of a list of elements like this is to convert it over to a matrix. Specifically, we'll convert the span over to what's known as the row space. So the span of the rows of a matrix. And if you do that, it will turn into this. Ooh. Right, and so note, row 1 of the matrix corresponds to the first element in the span, row 2 of the matrix corresponds to the second, so on and so forth. Right, so there's a natural matrix you want to make here, just smash these three together, but it turns out that's not really, like, the thing you want. Right, instead you want to create this, because as we learned, the row space of a matrix does not care about row operations. So you can go ahead and compute the ref of this matrix, and as we saw, that then gives us a much nicer thing to work with. Refs, of course, have a lot of zeros, and that gave us sort of a very nice, clean, simplified span to work with. All right, and if you compute the ref here, life is good. You do get a lot of zeros. But something interesting happens this time around, and we've already dealt with matrices that look like this, and we know that when I ref them, a big fat row of zeros shows up at the bottom. So if you ref this matrix, you'll actually get this. And so now something really fascinating happens. I have three things in my original span, and then I go to my matrix and I ref it. But note, I got a big old thing of zeros, but we know that scaling the zero vector doesn't do anything. It just gives you back the zero vector, and adding the zero vector also does not do anything. So now when I convert this back over to a span, something astonishing happens. Right? When I convert this back over to a span, yeah, let me make sure I type the word matrix correctly, otherwise I'm going to get yelled at. And I don't know if you can hear them, I got cats fighting in the background. Pretty good situation. Alright, so now when you convert this over to a span, what happens? Hey, it's a span now of only 2 vectors. I started with 3, but now my span has reduced. Ooh. Down to these 2. And again, as we noted, this span here is much better than the original. Oh my god, look at all those boxes. Right, this span, while certainly you can write out that it's the collection of all linear combos of those 3 vectors, that's not particularly informative, right? Doesn't give me a feel for what they do. But this method of converting over to a matrix, then row operating, and then looking at the span of the ref that you find, this gives you a much sort of a cleaner picture, or a much nicer picture of what the span actually consists of, because now when I convert this over back to a set, which I am currently doing as we speak, when I convert it over to a set, because it came out of a ref, there are so many... Oh my god, what happened there? Because there are so many zeros and ones now, when I go ahead and look at the span here, this set is much cleaner to work with, because now I have sort of this very nice form. I lost a minus sign, let me fix that, to what the span actually consists of, what elements are actually in my span. I've simplified it now, and it's much more readable, because now I know that the span of these 3 elements consists of all elements of R3, where the first and the second coordinates are free to be whatever they want to be, but the third one is dependent on the other. And if that looks familiar, it just so happens to be the one we saw last time. As an accident, I didn't do that on purpose. Alright, well, this time around, we noted something much more different, though. I had 3 vectors to begin with, but they collapse down like this. What's really interesting is before we had 2 vectors, and the span still consisted of 2 things after we refed it. They were different, but they give us, right, the nice, clean, simplified form. Here, though, we went from 3 and we reduced to 2, and that's quite astonishing. But why did that happen? Well, we know something about this matrix in here. Hey, we got a big fat row of zeros. What did that tell me about my null space? Oh, you hear the cat meow? Yeah. Well, a big fat row of zeros tells me that my null space is going to have non-trivial answers. Okay, now this matrix right here is not the correct matrix, so if I have these 3 vectors right here, now let's look at this matrix. So let's now look at the matrix that you wanted to make, which was the matrix where you just take your vectors and smush them together. Note that in the calculation of a span, that's not what you do. You do not smush them together, you use them to make the rows. If I look at this matrix, let me give it a symbol, A. Right, this is the natural matrix to make by taking these 3 and putting them together. This matrix right here, we already kind of know something about. not only are we going to look at this matrix, let's go ahead and compute its null space. Right. All right. And so again, remember the way to do this is to find its ref, its reduced row echelon form, and quite interestingly, the ref for this matrix, now note this is not the same matrix that we have here, but interestingly enough, it does end up having the same ref. And so as a system, right, we can write this out. So in particular, the associated homogeneous system that you would get out of this is as follows. Right, and from there we can read off that x is z and y is equal to negative 2z. And so the null space of A then is neatly characterized as follows. Hear that cat meowing. It's having a party. As follows. Okay. Oop. Oh, what's it yelling? Oh, I forgot my end equation. All right. So here we see some interesting things. Okay. So our three vectors here, 1, 4, 7, 2, 5, 8, 3, 6, 9. When we find their simplified span, we lose a vector. We lose information. And if we were to make the natural matrix associated with it, we find that its null space is not trivial. Ooh. Pretty exciting stuff there. And in fact, this is going to be our best friend here. Because note here, what does this null space tell me? Well, this null space tells me that there are non-trivial solutions to the associated homogeneous system. So in particular, let's note that a specific vector belongs to the null space. Now, obviously, the zero vector is always present in the null space, as we pointed out. And note that we have now a specific element that I can isolate in the null space, 1, negative 2, 1. Now, what does this mean? What does that mean, really? Well, it means it's a solution to the associated homogeneous system of equations for the original. So let's write that out. Right, what does that mean exactly? Alright, well, that means that that is a solution to the associated homogeneous system where the entries of the matrix A are, in fact, the coefficients. And as we're going to see, a little bit of magic happens here, and we sort of already touched on it, but this will make it way more explicit. Right, so when we were dealing with spans, as we introduced them previously, if this is in the null space, that means it's a solution to the associated homogeneous system for A, which means I have this. But if you take out your spectacles and look at this a little closer, that's in fact a linear combination. And note that what is it a linear combination of? Well, it is a linear combination of my vectors. and specifically the vectors that I started with. So I took my vectors and I made them the columns of my matrix there. And here we see that now, well, if I reinterpret the system as a linear combination, I've arrived at the following. I have found that my vectors 1, 4, 7, 2, 5, 8, 3, 6, 9, I can scale and add them and get the zero vector. Ooh, pretty exciting. Right, and note, what am I doing here? Well, I'm noting that something we pulled before, the way we were able to sort of deal with spans and work with them, well, you belong to the span of a list of elements precisely if there's a corresponding system that you can make. Ooh, pretty exciting. And these vectors, 1, 4, 7, 2, 5, 8, 3, 6, 9, we see a interesting fact here. This span we knew collapsed down to simply two vectors. What is that cat doing? You hearing this nonsense? And here we see that there was a linear combination of them that is equal to 0 with non-trivial scalars. Ooh, boy, what did we just find? Well, we found a pretty neat little connection. So, here we see that I can find these non-trivial scalars to get me to scale up and equal 0, and our null space there then had non-trivial things in it. And as we saw here, well, when we went to simplify the span, we lost an element. Right, and part of that is that there's sort of a linear redundancy here. Because this actually revealed something. I can isolate my first vector by itself, and by moving the other vectors to the other side of the equation, I'll find that the first vector was actually, in fact, a linear combination of the other two, right? You can add that over and subtract this over and get that. So our matrix here that we started with, so our three vectors here we started with, we computed its simplified span, and we found that, hey, it collapsed down to two elements, and by going to its null space and inspecting that, we discovered that the first element is actually a linear combo of the second two. So there is a linear redundancy going on here. So yeah, when I go ahead and try to simplify the span, I'm going to lose one of the vectors because one of them is dependent on the other. Oh, dependent. I wonder if that's, oh yeah, the topic for today. Hey, we made it. Alright, so we found the simplified span of these three elements, and then we investigated the null space of the associated matrix, and we discovered this interesting thing going on here. So that's going to lead us to the following beautiful definition. So, following this, we define Alright, so what was the key thing here? Well, the key thing here was that, hey, I was able to scale and add and get the zero vector in a non-trivial way. And because of that, right, note there was a non-zero scalar that you could sort of pivot on. So what we want is, hey, if I scale and add up and get 0, the only way that could have happened is if I have the 0 scalars. All right, and so formally speaking, we'll say that a list of elements in Rn are linearly independent if you can scale and add them up, and the only way that could have happened is if all of the scalars were equal to 0. All right, so let's get that definition up here. There it is. Okay, so note, a list of elements xm living in Rn, they don't need to be the same. All right, so this list will be called linearly independent if I could find scalars alpha 1 to alpha m, so that when I make the trivial linear combo, so if they scale and add up to 0, then the scalars had to have been 0. And note that this is going against this example here, because this is an example here. Right, what I wanted to happen is a not linear redundancy, because if I could scale and add up to 0 with non-zero scalars, then I can isolate one of the vectors as a linear combo of the others, which is what I don't want to do. Right, because that means that when I'm trying to span it, well, I'm really spanning too many things. There's a redundancy going on that I want to eliminate. All right, so that leads us to the notion of linear independence. Hey. And now, as we just sort of saw on display here, the following is true. All right, so let's get a bunch of facts for today. And this will actually finish us off, because we just need to compile the list of all facts of linearly independent things that we've now got. Okay, so now that we have this notion of linear independence defined, let's go ahead and produce a list of facts. Some of these we'll prove, other ones we'll just go, well, yeah, that's obvious. Oh, what is it yelling at me about? Alright. Alright, so we have got a definition of linear independence. Let's talk, what are some facts that we got here? Okay. Alright, so we've now got this beautiful definition, so note that we've already kind of let the secret out. So given a list of elements, let okay. So let's do the first thing that we kind of already noted, that there is a connection between linear combos and spans. So in particular, let x1 to xm be out of Rn, and then we'll let A be the n by m matrix with these columns as its vectors. Right, so column 1 will be x1. Note this lives in Rn, so that means there are n rows. And I have m of these, so I have m columns. All right, well, as we sort of see on display here, if you are in the null space, that means, hey, you've got a linear combo that's equal to 0. So linear independence is saying that a linear combo equaling 0 means all the scalars are 0. And so this would mean then that linear independence happens precisely when the null space is trivial. There we go. Right, we see that kind of on display here, right? If you scale up and equal 0, well, then you're a solution to the associated homogeneous. Okay, and if you're linearly independent, the only way you can scale up and get 0 is if all of the scalars were 0, and vice versa. So, hey, this gives us a just legitimate, immediate, obvious test for linear independence. You just go to the null space of your matrix. So, for example, as we just saw, our vectors here that we got are linearly dependent. in here. Right, these are linearly dependent, the opposite of independent, because, well, we just demonstrated that null space is, in fact, not trivial. However, as we experienced last time, if I drop off that last vector, if I only look at the first two, so last time we investigated these two, oh, that was a yelling at me about, oh, don't know how to spell the word equation. Classic. Okay, last time we looked at these two vectors, and we incidentally demonstrated that their null space was trivial, so let me type that out more as follows. Right, so if you wanted to use our new method here to compute the null space, so these two vectors are linearly independent, since if I smash them together into a matrix and compute its ref, I find that I have two pivot columns, and since I only have two columns, it means I only have two variables, and two pivot columns means that my variables have to be determined, and then in a null space situation, they would have to be trivial. Right. Beautiful. Okay. Cool. Great. So this gives us a turn the crank computational method of computing with whether or not a list of elements are linearly dependent or not. The easiest way to do this is to form the matrix with the vectors and then go after its null space, which again, you can determine if the null space will have non-trivial answers if you fail to have enough pivot columns. So here, with this matrix, we only have two pivot columns, but since we've got 3 columns overall, we would need 3. This matrix, however, has 2 columns, and 2 pivot columns gives us enough to ensure that the null space is trivial. Right, so note there's a connection here to the notion of non-singular matrix. Again, a non-singular matrix is a square one, so in particular, note as a consequence here we have So as kind of a consequence of the previous point, we find that there is another way of viewing non-singularity. Non-singularity was asking for the null space to be trivial, and now we see that another way of thinking of that is that your columns are linearly independent. And again, note that's just corresponding to, hey, you were trying to figure out the span of those elements in the first place, and now we're seeing sort of linear independence as a nice thing with the span, because a linearly dependent thing has sort of a deficient span. When you simplify it down, you get this. Incidentally, note these things that we got after simplifying the span are in fact linearly independent. Alright, so what are some other things about linear independence that are worth establishing here? So, a natural thing to do, and we sort of do this with span, is to kind of look at extreme cases. Any non-zero element on its own is by default linearly independent. And that's pretty easy to see, because if you have a scaled element equaling 0, then either the scalar was 0 or the vector is 0. So if you're non-zero, that forces the scalar to be 0. So a single element is pretty easy to detect if it's linearly independent. It's got to be non-zero. And following that, a single element being linearly independent, precisely when one of the elements, when the element is non-zero. So following that, if you have one of your elements is equal to 0, then it's got to be that what you have is linearly dependent. And that's pretty easy to see because in the ref there will be a column of zeros, meaning that there is a column that fails to be pivot. So the null space then was going to have non-trivial things in it. Pretty cool. All right, so that's a pretty quick sniff test. If there's something 0 in the list, then yep, you're dependent because you did fail to have enough pivot columns. And even more, following that, well, let's note something. We know something about the size of a matrix and failing to have only the trivial solution for your null space. So if you're in the situation where you have more unknowns than you have equations, we know that the null space has non-trivial answers. And in particular, that would mean that if you have a list in Rn where m exceeds n, then they have to be linearly dependent. Right, and that has to come out of the fact that, all right, well, if you make the matrix, well, the matrix has more columns than rows, more columns than rows. So yeah, then the null space has non-trivial things in it, and thus we see that'll get you the dependence. Cool. So that's pretty nice. So it tells us that in Rn there's kind of an upper bound for linear independence up to n. Right? You can't go any further than that. Pretty neat there with that. All right. And let's end today with an actual proof this time. And in particular, we'll bring us back around the span, and this will reveal a very powerful and important fact. So let's say you have a list of linearly independent things, and you have an element that lives in its span. Well, if you're in the span, then you're in a linear combination. But here we're going to see that with linear independence, not only are we going to have that linear combo, we're going to have a uniqueness. And it's going to jump me to the next page. All right, so if you have a list of linearly independent things, let's say you live in the span of such things. Well, if you're in the span, then there are scalars that you have to equal the linear combo of. That's what it just means to be in the span. But here we see they have to be unique. And, oh hey, unique answers, linear independence, hey! Alright, so let's actually do the proof of this. That's where we'll end for today. This will cover pretty much all of the linear independence stuff that I wanted to hit up. Got some nice examples of things, and beautiful definitions and some nice little consequences. But let's actually prove this. And this reveals that linear independence, following our example here, right, you could belong to the span, but really these two elements are the real star of the show. And now here we see that if you are linearly independent, well, the actual elements themselves can be used to not only generate linear combos, but they're also unique. Okay. All right, so first note by hypothesis, there have to be scalars with this property because you belonged to the span, right? If you're in the span, unravel the definition, that means there are scalars so that you're equal to it. I'm claiming they're unique, so now, suppose you could find other scalars with the exact same property. So, in other words, you could find scalars so that x was equal to beta 1, scaling x1, all the way up to beta m, scaling xn. Okay, so I'm claiming uniqueness. Now what do I do? Well, subtract these two equations. Well, if you do that, you'll have x minus x, which is equal to 0, but then, if I were to subtract these two equations from each other, excuse me, if I were to subtract these two equations from each other, well, alpha x1 minus beta x1 will just be alpha 1 minus beta 1x, because we know we can distribute as follows. And hey, look, I've got a linear combo of my vectors equaling 0. By definition of linear independence, you have to have that all of those scalars are equal to 0. That's literally just the definition of linear independence. All right. And therefore, the alphas and the betas all need to be equal to each other, guaranteeing the uniqueness that we were promised. Ah, beautiful. All right, so there we go. Now we have seen that, hey, if you have a list of linearly independent things, and if you land in the span, there are unique scalars that work. But, while as good as this is, it's a little, I don't want to say defeating or anything. Well, this says that if you belong to the span, there is a unique element you can find. And as we sort of already pointed out, well, if you belong to the span, there's a system of linear equations associated with it. Linear independence is guaranteeing that that system has a unique answer. Now, is it telling me how to find it? No, right? I have to go through and get the ref of it. It would be great if I had a type of linear independence where I actually had formulas for the alphas. I wonder if that's what we're going to go for next. All right, that's it for today. I'll see you next time.